Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. I'd like to go ahead and get started. My name is Lee Dirks, the Director in External Research for Education and Scholarly Communication. I'd like to welcome you to the session on data and visualization, or as I'm going to call it, really cool stuff in the Berkeley area. The first speakers are, is it John? Is it just going to be you? Or yeah, okay. So our co-presenters, but one folk who will be standing up will be John Kunze from the California Curation Center to tell us about some interesting work and projects they have going on. So I hand it over to you, John.
Thank you, Lee. Let's get this in my pocket. Well, good morning, and thank you all for coming out here at the crack of dawn to listen to some PowerPoint. Really happy to be here with my colleague Tricia Cruse to talk to you about the exciting Excel add-in project that we're working on and some related projects. I'm also pointing out Rachel Hugh, who is we're very fortunate to have helping on at least two of these projects. A brief introduction to who we are. We are the University of California Curation Center. We're a unit of the California Digital Library, which serves the 10 UC campuses. It's about 250,000 students, 134,000 faculty and staff. We work collaboratively. We're really very much about community and collaboration. We work with libraries, data centers, museums, and archives, and increasingly directly with faculty and researchers. And that's particularly going to tie into our use of data, because libraries are not the first stop for most data scientists. So we want to encourage that, but in the meantime, we're going to be dealing with them. So we offer this community of shared concern and practice, services to both distribute and to gather diverse experience, expertise, and resources. And then we provide robust, innovative, and cost-effective solutions to basically deal with the effects of inevitable disruptive change. I barely need to remind this audience as motivation that data is treated as a second-class citizen in the scholarly record. There's a gap between how data and traditional publishing traditional scholarly output is produced. Research data is difficult to manage after the project funding ceases, but for the journal article, libraries keep it safe. Research data, you don't know who has it, how do you get it, what is its impact, and where is it. But all these problems are solved in the libraries and archive world. You can monitor impact, you know how to find it, you know that some archive has it, some archive or library has it. So for the project, the Excel add-in project, the large overall goal that we're approaching is how to promote data publishing, data sharing, and data archiving. And our community is essentially the data producers drawn from the global community, but we're going to concentrate on the UC community and the Data One, the NSF Data One community. Data centers and archives, publishers, museums are also stakeholders. So this is a huge and complicated undertaking. So we've chosen to chip away at the problem with a variety of approaches. And all of these approaches are going to require sort of community engagement. Nobody can do this on their own. So one approach is analysis. We're conducting a study with help from the Moore Foundation to study data documenting practices, essentially the formulas, techniques, and algorithms that you can't publish in a regular publication, but would like to. This important information is being lost, along with credit, the substantial credit for the effort that goes into data production. Another approach is discovery. We're founding members of the DataCite consortium working on citation standards and persistent identifiers for data sets. We're involved in another approach is the direct production and reflection of data through our participation in the Data One NSF-funded data network. And then lastly, what I want to talk about today is the means. This is the open source Excel add-in that we're trying to directly contribute a tool that we think will make a big difference. There's some related milestones I'll spend a tiny bit of time on. Very recently, we've released an EZID identifier service for persistent long-term identifiers for DOIs and ARC identifiers. We have a new Merritt repository infrastructure based on our Curation microservices, which is making a little splash in the library world. Maybe, I'm not sure if you've heard of it. I'll say a little bit about that later. We've produced some data management guidelines for the University of California, and these are about to be made public any day now. And there's also this Jove 2 format characterization environment, formerly a format validation environment. Basically, it goes and inspects files and reports deeply on the format and conformance. While this work was being done, the framework for it was created, and it was so well documented in its pre-release phase that some group went off and did a validation unit for NetCDF. And it's all done and complete, and said it was easy to do. So community engagement happened even before this was fully released. So here's this very subtle slide about, in case you're wondering if this is an important problem. With global warming and health epidemics, economic crises, the planet is at risk. If the scientific record is at risk, so is the planet, because results can't be reproduced. So you can choose better archiving, data publishing, archiving, and sharing, or so why Excel and why an add-in? Well, spreadsheets hold an important class of data, a very important class of data that I keep hearing the word long tail used at this conference, and some people would call this long tail data. It's not big, but there are many of these smaller data sets. The downsides are well known. Excel is not a database management system. It doesn't scale particularly well, but nonetheless, it's everywhere. It's very familiar. It's easy to use, and scientists are using it and will continue to use it. If we can create an open source add-in that extends Excel functionality, we can leverage a huge installed base. So as we were first thinking about this project with Lee and Tony, we were bandying about some ideas. It quickly became, we realized there's a blizzard of good ideas, and that we were not qualified to pick which ideas they should be. So we're going to assemble a group of researchers who actually work with data and have them tell us what the best ideas are. And we'll interact a little bit we'll understand the development costs, and we'll probably use some formula like low-hanging fruit to pick a few things to develop among the many features. But some of them are, standardized column headers, versioning, which is not present in Excel, standard date formats, which you've probably come across as being a difficult problem. Automatic archiving, or at least the ability to save your data set directly in an archive would be great, and along with persistent identifier assignment. People have talked about misuse of too many of the features of Excel. It'd be nice to install with an add-in to install some speed bumps to discourage things that would make archiving difficult, in particular macros. Other potential add-in features, and I say again potential because we're not selecting these, we have focus groups that will select these. A workbook builder, which will allow you to go to some globally defined set of standardized workbooks and make selections that will have been developed by domains. The ability to export metadata in a standard format. The ability to select from and add to globally shared definitions of terms, and the ability to import term descriptions from shared vocabularies and annotate them locally. So our project partners, of course, Microsoft Research will be providing the funding and the developers. The University of California and the NSF Data One project researchers will be involved in help us gather requirements and test the compliance with those requirements. Our initial focus will be on the earth sciences requirements. We realize this could be applicable to many places, but we need to focus a little bit to start with. We at the UC Curation Center will provide project leadership, manage all the communication between the developers and the testers. Project outputs, there will be 4 outputs. A tested, fully functional, documented Excel add-in, a publicly available compilation of the gathered requirements. We'll be doing outreach in the form of conference presentations and publications, and notably, from early on, we will release open source version as we develop via Codeplex. And finally, we hope to establish a community that can carry on the work, because think of all the functionality that we will not have been able to do, but will be next on the agenda. Our work plan is to essentially at each stage engage the community, assembling participating researcher groups from University of California and Data One. We'll interview them to derive our initial requirements and then convene focus groups to iterate and draft the final requirements. Development will be iterative, as will testing and feedback at each stage. At the end, we'll do final testing and documentation and a final code release. So right now I want to spend a slide each on the other sort of backing approaches. As I said, we are chipping away at this very complex problem, and we hope to make progress on different fronts. And the analysis front, I want to mention this cross-domain study we're doing to look into how this informal appendix material is created by scientists. This is the stuff that you can't publish. It's techniques, formulas, algorithms, methods, maybe software, tables of results that sit behind graphs, full documentation of the data sources used, as well as full credit to the data producers. This is the stuff that you need, because if you can't reproduce the science without this stuff, but there's no room to publish it. So this stuff is not published and therefore not archived. And this work, again, is funded by the Gordon and Betty Moore Foundation. We're also a founding member of the DataCite consortium. It's a global consortium that is setting standards for data citation and persistent identification of data sets. So we're developing registration services and identifier services for this, and I'll say a little bit more about that. We're also a member of Data One. We're gearing up to become a member node, contributing data to this global network, and possibly becoming a replication partner. Here's sort of a sense of what we do in Data One: build on existing cyber infrastructure, create new cyber infrastructure, and create communities. This is a key part of our strategy, and they're providing enormous expertise for a number of projects we're working on. So in these sort of related areas that we're working on, we have this new EZID identifier service, so identifiers for the long term. Its core functions is it allows you to create persistent identifiers, DOIs, and lower-cost ARC identifiers for now. This is intentionally scheme agnostic. We feel that resolution and identifier support doesn't really need to be tied to the scheme, and we're going to have to deal as a library with all the schemes. So handles, URNs, we'll be prepared to deal with ordinary URLs and be able to centrally manage those as well. So we can add an object location or a resolver target. For those of you who know about resolvers, you can add metadata, arbitrary metadata, as well as guidelines for standard DataCite metadata. And you can update that as well. So this kind of, where would you use EZID? It will be assisting you in data-intensive research, help you get preservation-ready identifiers, sometimes long before you're ready to deposit the object, maybe years before. It would be really nice to have an identifier that you can use right away without having to rename it when you deposit it in an archive. So it can help research teams coordinate their work and communicate internally. It facilitates data publication for obvious reasons. It's useful to have that identifier when you publish. Also, increasingly, as we've talked about, you've heard the federal, the funding agencies are requiring data management plans, and this feeds right into it. You need a persistent identifier. Quick screenshot. This is a couple of tabs up here. If you go and visit the service, anyone, you don't need to log in. You can click on the Help tab and actually create identifiers and play with them, and they resolve just like long-term identifiers. So I encourage you to play with it. Another key component is the Merritt repository service. This is a reference to Lake Merritt, which you can see from the break room right across the hall. It's a landmark in downtown Oakland. It is essentially a new repository service that provides very cost-effective solution for sort of discipline-agnostic data. It's open to the UC community and others. Right now, the UC community. The software is available so that you can host this yourself, locally, or you can use our hosted service. It has a UI, user interface, and an API, as does the EZID service. So you can set your scripts against it or use it as an ordinary user. You might ask, why do we need another repository system? Well, we've made enough noise about this elsewhere. I won't spend a lot of time, but we've got this thing called Curation microservices, sort of break down the whole monolithic repository approach and think of it as a set of composable subservices that are very low commitment, very easy to buy into, and you can mix and match and combine them to create repository function. It's very file system centric. We like the file system. We believe in it. Everyone's got one, and you all have tools that you can manage your objects with. And it's very simple. So these are the strengths. This is why another repository system. We've just about finished our data management guidelines. This is in response to the NSF and NIH requirements. We did a nice survey across a bunch of existing data management plans. There's actually 8 of them. One of them is not here. And so to analyze the strengths and weaknesses of each one, and hopefully we did a nice eclectic mix. And this was done with the help of the Data One and Data One interns that helped us with the analysis of this. So to close here, the gap between traditional publishing and data publishing. With this Excel add-in and other projects, we think that we're working to empower researchers by enabling them to find, cite, and get credit for the research data sets with confidence. We support data centers by providing workflows and standards for data publication. We extend libraries' historic mission and collection building activities to data sets and help them to preserve their institution's research investments. And we enable publishers to enrich their publications with the full story. Are there any questions?
Thank you, John. Questions?
So this may be a little tangential. Could you go back to the work that the interns had done? So this is in response to the NSF requiring you to have a data management plan.
NSF and NIH.
Right.
Yeah.
So they ask you for some stuff. Do they ask you the right questions?
We don't really know. I'm not sure that they really know.
They give you 2 pages.
Right.
Either hang yourself or...
Right, but as somebody that that is trying to look at how you properly curate scientific data, you may have a view on the questions that they're asking you, and maybe they're not the right set. Maybe there are other things that you know that you're going to do that you're not documenting to them because they're not asking for it.
Right.
But I'm interested in that bigger set.
Well, we are interested too, so we hope you will give us feedback and tell us where the gaps are in our plan.
No, I want you to tell.
But I thought you had the idea.
No, indeed, I want us to be able to tell NSF that the set of things they're asking for is incomplete. If it's incomplete, if it's fine, then great.
Well, I think my guess is that NSF is going to be reacting to. There's going to be a sort of a ping pong game where guidelines will be produced, NSF will react, they'll actually up their requirements or clarify their requirements. So I hope that happens. And
Hi, this may be way beyond scope because it's too hard, but are you looking at making Excel an OData producer rather than a consumer?
and OData, by OData, you mean?
The open data protocol for
So-
publishing. If you don't know about it, don't worry. I mean, the share.
Yeah, no, I mean-
So, so it's out of scope of this project.
No,
Oh,
not
okay.
at all. Nothing's out of scope. So I mean, so we're going to start with the assumption that XML will be produced, I think, and it'll really be dependent. It'll depend on what the researchers' requirements are, and we hope that in our development, we won't paint ourselves into a corner and preclude other reasonable requirements that we can't get to. So it'd be really good to know about the requirements that you're thinking of.
Because there's a real hole in the OData ecosystem, really, in terms of producers, I think.
Yeah.
So I was a little unclear as to what's available now versus the calendar for what's coming. So what, like if I went back to my room and with my laptop, what could I do today?
So this project has not started.
Okay.
We haven't signed the bottom line. Is the deal hasn't completely closed, so it's not started yet. You won't find anything except, I don't think we've published anything on this.
So the Excel project we haven't started yet, but the EZID service is available
ready.
now.
Oh, yeah.
Merritt is available now. The
Yeah.
data management guidelines, hopefully by the end of the week, will be available.
Okay.
So
And the Jove 2 stuff as well.
Cruse is available now.
Okay. That answers.
Oh, thank you. I was concentrating on the Excel.
Hey, a question about the Excel add-in. You mentioned that you still want to gather requirements with researchers. I'm wondering.
I should mention we haven't started gathering requirements yet.
Okay, haven't started. So, how did you come to a technology decision before the requirements are known?
Little chicken and egg. I think the technology decision we've made is Excel, and because it seemed right. The number of researchers using it, it doesn't. It seems a little bit of a, yeah. We're comfortable with that decision. Are you uncomfortable with that decision?
Well, I just think that there are other alternatives. Maybe it's a web service that creates Excel templates for the researchers. Who knows what it could be? I don't want to presuppose an answer. I just wonder why the technology solution is the starting point rather than the next.
It doesn't. Yeah, there may be web services that we could make Excel callable from web services so that this could be done. But there has been some talk about sort of a brokering, how to make Excel look like a database to a set of web services. So there has been some discussion of that, and I don't think that's off the table. So.
One last question.
I'm just curious if Phil Bourne yesterday talked about having DOIs for people and ORCID, and I was just wondering if you would considered, not just uniquely identifying the data, but identifying the researcher who is associated with it?
Absolutely. We're doing that now. So every account holder has an account name and a password, which are transient, but they're going to get a unique identifier, which we're not talking about publicly, but I am talking about it publicly. We're not documenting that because we're...
Yes, we are.
But that's...
You want to stop now.
So I'll have to go shoot myself now. So. But it's no big secret. It's just that we're pretty sure we can do some really good stuff with it. And we're being very careful up front to uniquely identify each user of the system, each contributor to the system.
All right. Thank you very much, John.
Thank you.
Appreciate it. And so I'll invite Roland and David up to maybe get me a few minutes of setup. So I'll hand it off to David and to Roland.
Okay. Thanks for being here this morning. Welcome for those of you not from the area, welcome to the Bay Area. It's usually not this hot, but we didn't get summer this year, and so you're kind of getting our summer, and you're lucky to be here at this time. I'm going to talk to you a bit about Chronozoom. And Chronozoom is a project we've been working on in our group, helped out, and we've been helped out by Microsoft quite a bit on this. All the world's a stage. This can probably be taken as the view of many historians. Historians view people and people through movements, global movements, as being actors in history. But they tend to view the physical world around them as just a stage on which human history is acted out. In our group, we're geologists, and so we kind of object to this view because we think that the Earth has its own history, that the Earth is that it contributes to this longer, the history of humanity. So today, what we want to do is talk to you about Chronozoom. And my name is David Shimabukuro. I'm here with my colleague, Roland Saekow, and both of us are researchers in the group of Walter Alvarez, who's in the Department of Earth and Planetary Science at UC Berkeley, on the other side of the town. And so we've been working with, Walter and Roland developed this piece of software, Chronozoom. I've been involved with Walter on a concept called big history. And so over the next few minutes, I'm going to explain, we're going to talk about a few things. The first is going into this concept of big history. Before we get to the technological, the technology behind Chronozoom, we want to kind of set you up and kind of tell you guys what problems led to us dealing with Chronozoom. We're going to go into the particular problem called the timescale problem. How do you illustrate history? How do you illustrate human history? How do you show vast time periods from 1 year, 1 day, all the way out to billions of years, which is the age of the universe? And we're going to talk a little bit about, we're going to spend the last half of this talk on Chronozoom, and we're going to give you a little sample of version 1. We're currently working on version 2 with Microsoft, but version 1 is a delight. Big history has recently got a definition. So big history is a history of everything, to sum up concisely. Big history is an attempt to understand in a unified and interdisciplinary way the history of the cosmos, Earth, life, and humanity. So the cosmos, Earth, life, and humanity, these 4 realms will kind of be the focus of big history. And it was invented by a professor, one of our colleagues at Macquarie University in Sydney, David Christian. And David Christian's an Oxford-trained historian. He's a specialist in Russian history. His interest in Russian history ranges from the Silk routes all the way up to modern times. His most recent work was called Living Water, and it's a history of how vodka played a role in the transition between communism and capitalism in Russia. And I'm sure that the field research for that was very, very interesting. Now, in his role as being a professor of Russian history, he naturally became interested in something called world history. And world history is a relatively new field of study. It's a way of viewing the world that instead of looking at histories in terms of nations or regions, you look at an integrated whole. And this is important because, as we know, that globalization is not a recent thing, that for millennia, there have been transition or a transfer of knowledge and goods between different cultures. And so when you look at one culture, you're stuck in a box. And world history gives you a way of looking at a larger context. So David's been involved in this world history concept, and he was teaching a class on this. And when he was putting the notes together, he started with day one. He said, where should I start world history? Well, the natural place to start it is with the beginning of civilizations. Well, civilizations, is that really the beginning of all of history? No. Let's push it back a little bit further. So he went to the beginning of agriculture and kept on asking this question. Well, is this really the proper place to start it? 5 million years ago, is this a place to start it when humans became upright? 3.9 billion years ago, when life started, should that be a more proper place? Maybe 4.56 billion years ago, when the Earth was formed. And as a geologist, 4.56 billion, that's a nice number. I kind of like starting history at that point. But he pushed it back further. No, 4.56 is not the start of everything. The only logical place to start a history course is at 13.7 billion years ago, during the Big Bang. And so this concept of big history, the history of everything, started. And this has been a really spectacularly successful concept. It's being taught at dozens of universities around the world. And at some, including the University of Amsterdam, it's one of the core classes in a curriculum. And hundreds of students take it. And it's been really successful in giving students a context for each of their specialized, compartmentalized knowledge and seeing how that their major, their specialization is in terms of all of history. Now, I mentioned that we are working with Walter Alvarez in the Department of Earth and Planetary Science at Berkeley. Walter is in the middle. He's most famous for his discovery, for his work at Gubbio, Italy, on the Cretaceous-Tertiary boundary. This is a thin clay layer, synchronous with the instant at which the dinosaurs disappeared from the Earth. And Walter was part of a multidisciplinary team which studied this layer and eventually concluded that it was caused by a meteorite impact. And this theory was later confirmed in 1993 when the actual crater was found in Chicxulub, Italy. So I think work as a geologist on this particular project gave Walter two unique things when looking at history. The first is how to think of history in an interdisciplinary fashion. Walter's a geologist. His father was a physicist. He worked with nuclear chemists. This theory of the dinosaur extinction, you had to deal with paleontologists. You had to deal with astronomers. So you dealt with everybody from the physical sciences to the biological sciences, and you had to get them to communicate. The second thing that this theory, I think, taught to Walter was how to think of time on vastly different scales. We're talking about an event 65 million years ago, but that clay layer at the Cretaceous-Tertiary boundary is only hours to days worth of deposition. And so you had to kind of switch your brain between these two different time scales. So I became involved with this concept of big history by being Walter's teaching assistant when he first taught this in 2007 on campus here. And this was taught as an Earth and Planetary Science course, but it was also taught as a Letters and Science course, as an interdisciplinary course, to get as many people involved as possible. And so we called it Cosmos, Earth, Life, and Humanity. When I was involved in teaching this, it was really exciting to see an art historian and a physicist talking about what the Big Bang meant, or seeing a classics major and a chemist talk about globalization and industrialization. And so everybody brought their specialties in, but once again, they had context to see it, to see what was going on. And the joke about this course was that we covered everything from the Big Bang to present. So we had lectures on stellar formation. We had lectures on globalization. And so these are all vastly different things. But the joke was that in a 15-week course, if you're covering 13.7 billion years of history, you cover about 1 billion years per week. So think about that for readings or for any history course that you've taken, 1 billion years per week. So while teaching this class, we realized we had a problem. And so this is going into what we call the timescale problem. And as geologists, we're used to dealing with these vast quantities of time and saying, how do you explain this to students? And the way we get them to understand millions of years or billions of years is we reprogram their brains. Our natural frame of reference is maybe days or years. And for a geologist, you kind of tell students that, well, let's start using 1 million years as your standard. And once you put things in terms of millions of years, then the dinosaurs going away 65 million years ago is, that's an understandable concept, 65 of million-year units. However, in big history, this doesn't work because in addition to dealing with millions of years, we're dealing with thousands of years, we're dealing with years, and so we needed to figure out a way to illustrate this problem. So you can see here that human history is 5,000 years, whereas Earth history is 5,000 million years. You have a million times difference between these two units. To go into this further, we can see that if we look at cosmic history, it goes back 13.7 billion years. If we look at Earth history, 4.56 billion years. If you look at life history, we don't have fossils from 4 billion years ago, but we have isotopic evidence of life from that far back, carbon isotopic excursions. Human prehistory goes back to Ardipithecus ramus, the first upright hominid, about 5 million years ago. Human history, the traditional realm of historians, goes back about to the beginning of written language and possibly further into archaeology, about 5,000 years ago. And these scale bars, the upper two are enlarged so you can see them on the screen. So as a scientist, how do you deal with this? How do you illustrate it? Well, as an undergrad, I was a physicist. Walter worked with physicists. So physicists, when you're dealing with these quantities, you think in terms of the log scale. And so we tried putting this up in terms of logarithmics, and this is just not a very useful diagram. The invention of writing is right adjacent to modern humans forming about 5 million years ago, which is kind of near the dinosaur extinction. And so this approach doesn't quite work. But let's modify this a bit and see how we can use this. Can we use this concept as logarithms, basically of zooming in, as something useful? And so what we'll do is we'll create a timeline. Here it's labeled 1, and that's all of history, back to the Big Bang, 13.7 billion years ago. Then we'll take a small portion of this and enlarge it and look at the last 2.5 billion, let's say. 2.5 billion is a useful number because it's the Proterozoic. It's a time period at which all of modern plate tectonics has existed, and most of life history has existed. And so if we're plotting vast geological events, we can put them on this timescale. Now let's create another timescale then. And this next timescale will be taking 10% of this, the last 250 million years, and expanding it to fill up the entire width of screen we have. And so over here we have 2.5 billion. Here's our newest one, 250 million. And on this we could plot the Mesozoic and the Cenozoic. It's the age of dinosaurs and the age of mammals. Then once again we can take 10% of that and maybe expand it out to 25 million years, and so on. So we could create different timescales depending on what we want to talk about. If we're talking about geology, we can use these timescales at the bottom. If we're talking about the transition between primates and humans, we can use these upper two. And further on, we can create timescales going up by a factor of 10. And if we want to talk about a human history, we can use these upper timescales. We can talk about modern history or history going back 2,500 years and basically choose our timescale. And so this works. It doesn't give you an integrated view of knowledge, though. And it's a little confusing. I mean, you're looking at this, and you conceptually can see what's going on, but it doesn't really you don't get an intuitive feeling for what's going on. You don't get an intuitive feeling that that upper time scale is some billion times smaller than this, this time scale over here. And so this is the problem that we had with big history, that we had to switch between very small time scales, days to years, and billion-year time scales. And that's where a technological solution came in. And so Roland Saekow was an undergraduate student in Walter's class, and Walter had people doing final projects. And so Roland kind of saw this problem, and being a product design major, tried to come up with a technical solution. So, Roland?
Perfect. So that's what we came onto the scene with. And these are the problems. I'm just going to recapitulate one more time. We've got terrible distortion from these logarithmic plots. It's a non-interactive experience, so you can't really choose what you want to browse to. And yeah, of course, there's no way to browse. So whatever the timeline was designed to do, that's what you get, and that's what you have to go with. So those are the problems. And Walter and I spent a lot of time thinking about how can we improve this with some sort of technological solution. I grew up fortunate with all these computers and games and so forth, so there must be something that we can apply to this. We have ways of seeing the Earth. We have, with Worldwide Telescope, ways of seeing the cosmos. Why can't we see time on the bigger scale and step back? So as you often have to do in big history is you have to think big. And so what we're thinking in the final idea that we settled on, and what I'm going to show you today, is a continuous zoom. And that is, if you have the Big Bang here to the present, could we go from this scale, billions of years, and zoom down to a single day? Could we do it? And so, of course, to do that, we need to calculate zoom factor. So let's look at the last 5 million years, when humans were first upright. There's the earliest evidence for that. And let's go down to a single day. Let's see what that would take and if we can do that. That zoom factor comes out to be about 1 billion. So if we were just going to tackle our Chronozoom project and just make it go from earliest human to single day, that would need 1 billion zoom factors. And I'll make a little more sense of that in a bit. But let's go back farther, because as David was talking, it goes back to Earth history. So 4.567 billion years to 5 million years. Notice how we went from billions to millions. So that zoom factor is 1,000. So we're adding another 1,000 on top of that billion we just had. So keep that in mind. And of course, we go back. We're thinking really big now. We're saying, let's go to the universe scale. Let's go to the Big Bang 13.7 billion years ago. And let's go to a single day. What would that take? What would the zoom factor be? Well, that turns out to be 5 trillion times. Okay? So 5 trillion is a crazy number. So we're like, what is that? So I went to my favorite tool. I went to Photoshop. And so I was like, OK, Photoshop, let's make the biggest image we can possibly make. Okay, and that turns out to be 300,000 by 300,000 pixels, which is about 90,000 megapixels. Okay, a lot of our cameras shoot 10 megapixel pictures. Think about 90,000 megapixel picture. That turns out, and when you zoom in all the way, the maximum zoom we get is 6,400%. So that's nothing. That's like a tiny sliver in what I need. So Photoshop wasn't going to cut it, and we had to look farther. So we came across deep zoom technology, which Microsoft is all involved in and taking to the next level. So with Sea-Dragon deep zoom technology, I'm going to show you Chronozoom. Before we get there, let me just define the goals of the project. Obviously, it's to see all the scales, so without a step-by-step, but actually see all the scales at any time. It's going to let you browse time. It's going to make history relevant to you. You can choose where you want to go into it. Of course, that means it's going to be highly interactive. You can zoom in and out in any part of it you want, leave a part you don't like. And more recently, you have this ability to compare data. So we're going to put all sorts of data that is time-related. So imagine climate data next to Roman history. What are the correlations between that? Things that are completely unrelated, you could possibly put together. So teaching and research are the 2 big uses we think Chronozoom will have. And this is what it looks like. So I'm going to point out the different features of Chronozoom before I go and we start zooming around in it. First of all, it goes Big Bang to present like a normal timeline. It's just fatter here because we've got all sorts of different time scales. Let me blow it up a little bit here and focus your attention up on the top. This top feature is what we call the navigator. The navigator looks just like what you saw Dave showing you earlier, and it shows cosmic, Earth, life, human history, and of course the last 2 are enormously exaggerated. But this is a navigator because you can click on any one of these bars and it will zoom you to those. So they're like shortcuts. Also, you see that gray bar on the top there? That's your current view. So if you zoom down to Earth and life history, that gray bar gets smaller. So it's a kind of a small visual aid. Right below the navigator is the time ruler. The time ruler is the most important part of Chronozoom because it tells you where you are in time. It's the thing that ties everything together. So on the cosmic scale, of course, everything's in billions of years. But this is dynamic. So thanks to some amazing work that the Live Labs team did, as you zoom into time toward the present, and you go to, say, Earth history, well, that will automatically change to millions of years. And down to human history, it'll be in years. So it'll be things that you can relate to. And of course, the last thing you're looking at here is all the data sets. So every row here is a different data set. In this case, we're looking at all of cosmic history. So we've got things from dark energy and accelerated expansion of the universe to the history of metallicity. So everything is just a separate data set. And these are all examples for the first version of Chronozoom. So that's the basic layout. We're looking at all of Cosmos here. And you can see in this white box here, that's Earth history. So again, we can see it's a third of cosmic history. So let me go ahead and give you a demo. So here I am. We're just running this in a web browser. Everything you see me doing today, you can do this at home. This is already live running on the web, and I'll give the web address out a little bit later. But what we're looking at here, this is the last day of the year 1989. So this is right before the millennium is going to be coming, and all those Y2K theories are going to be tested. So this is that instant right before, okay? Because this is the present, and you can see my time scale up here. What I'm going to do now is I'm going to slowly zoom out, and we're going to see all the months and so forth. So let's do that. So watch as that day disappears. There's all the days in the month of December, and all the months in the year 2000, in the 10th decade, and in the 20th century. Okay, so this is the 20th century, and you can see that single day has already gone into less than a pixel. It's gone. But we're just getting started because obviously human history goes back much farther. So let me keep zooming out here, and I'll use my shortcut here. So I'll click on human history. And so there's the 20th century, right in that little box. And so this goes back the last 3,000 or 4,000 years, and we've put Egypt in here just as an example. So you can see, let me go down into here, for example. I'm just zooming with my scroll wheel here. This is all streaming over the web. That's why you notice it's just sharpening as I go in. And what this is, once it sharpens, that is the pyramids. So you can see when the pyramids were made and who made them, who were responsible. So let me zoom out here again. So this is already many factors of zoom, more than we could do in any existing program, and that's why we use deep zoom technology. But again, we're just at the start of our problems because we're going to go from human history, and now I'm going to go to human prehistory, so as early as the first upright humans. So let me go ahead and click on that. So all of that's disappeared again in less than a pixel. And now we're in millions of years. So we've left the world of years, and now we're going back about 5 million years. The famous fossil Lucy, right? There it is. There it is for perspective. And Ardipithecus ramiges was more recently discovered. And Homo sapiens were over here. And so that will sharpen up once you give some time. So that's the last 5 million years. And now we're going to go to the billion-year scale. We're going to go to Earth and life history. So we're going to go all the way back. So that's all gone again. And now we're on the scale of billions of years. So this line here, this is as far back as the formation of the Earth and the solar system, our sun, shortly just before that. So let me go back one more time. This is another factor of 3. And this is all cosmic history, which I showed you before. So the Big Bang is over on this edge here, and we're going toward the present. So that's what it's like to browse through time using Chronozoom, using zoom at a maximum scale that is almost incomprehensible. We just did a 5 trillion times zoom, 5 trillion x zoom. Let me just show you some of the episodes that Dave talked about before we leave Chronozoom. What I'm zooming up into here, and we'll see if the internet pulls through. All these little arrows here are impacts on the Earth. So this is taken from an impact crater database. And the larger the arrow, the bigger the impact. So this Chicxulub one here, which would have loaded, that's the one that took out the dinosaurs that Walter worked on. So there it is for context. And you can see it's a very recent thing. But if you go back, you can see there are even bigger ones than that. And for comparing data, this is what I was talking about. You can see all these different rows of data going left and right. There's a possibility you could see what does this line up with and correlate to certain other events. So that would be interesting. The last thing I want to point out is an example from life history. So what we're looking at here, this is the family tree of humanity. This is based on DNA from a fabulous book called The Time Tree of Life. And what we're looking at here is starting from our last universal common ancestor, and you can see everything branching off. Here's archaea and so forth. And the way this works is every bar that goes off to the right on the bottom, that's when things are split off or we're divergent from us. And everything along the top edge goes towards us. So I'll zoom in here, and let's go down to this more complex one here. This would have showed the primates coming onto it, but our internet is not up to spec right here. And eventually that would have gotten you back to human prehistory. So that in itself is a 1,000-factor zoom right there. So let me just take you back to the present day, which we're calling the year 2000 on this scale here. Okay, we're back to Egypt in the second millennium, in the 20th century, and well, our internet's not going to cut it for this. So that's a quick look at what it would be like to browse the timescales. Before I leave this, I do want to show you some things that we're working on next. So you've already seen the incredible zoom technology that we can do. But how can we apply this to pictures? So we recently went out to Italy. We were just there in August. Some people in this room were there with us. And what you're looking at here is an outcrop. So this is a part of the Earth where all the layers of Earth are just kind of cut out and perfect for geologists to go up and see. They can see the individual layers and date things and so forth. What we did is we actually brought some special camera equipment with us, and we shot a gigapixel image. So we shot an image that's 1,000 megapixels or more. So I'm going to save us a little time here, the zooming, and I'm going to zoom into a kind of a thin slice here. Okay, so we're looking at a thin slice of that rock layer now. Okay, we can look around in it like this. Same thing, just scrolling in and out. And let's see. If I zoom into any one of this part, so you can see this is already more than a standard camera could do if you just pointed at a rock face and took at it. You can already see these fine details. Again, this is over 1,000 megapixel image. Okay, but you can keep going in. I mean, you could count these little guys if you needed to. Okay, and there's new work on cyclostratigraphy, which possibly means we can date time just by looking at these layers. So that's really interesting. And if you don't care about rocks at all, you can look at this. You can look at these plants, for example. You could count these veins on these leaves if you wanted. So there's some really cool promises for this deep zoom technology. So that's Chronozoom in a nutshell. And there's the website, chronozoomtimescale.org. Everything we tried out today is available on the web, and hopefully you have a better internet connection than I do. You can see all the scales. You can browse time. It's obviously highly interactive. And things we're working on for V2 is this comparing data thing. So how do we get more data sets into Chronozoom, let you put your own, and compare them with other ones next to them? And, of course, I want to thank everyone on the 1.0 team. This was done in April between the Live Labs, Microsoft Research, the Berkeley Intellectual Property Office, and, of course, UC Berkeley Renaissance Geology Group. So thank you so much. And if you have ideas, data sets you want to see in there, please email us at chronozoom@berkeley.edu. Otherwise, go and try it out and get a sense of time for yourself. Thank you very much.
Great job. So before I even said anything, hands have gone up. This is great. So are there any questions for Roland and David?
So Dave is the geologist. I'm the non-geologist. So direct your Earth history questions to Dave, please.
Hi, Joe Futrell from NCSA. We need to talk because at NCSA, our Medici system uses Sea-Dragon extensively to provide zoomability. So we have a bunch of services that we've built around Sea-Dragon and a bunch of and the ability to annotate in RDF, so we can associate data sets with zoomable stuff.
Sounds great.
So we really should share some technology.
Definitely.
And my question for you is, this has been done in the context of history, and you talk about every time scale except for seconds, microseconds,
right,
and such like that. So we have use cases where we have experimenters that are doing streaming data. And so it looks to me like the stuff that you're looking at now is a relatively static set of images.
Yep.
Have you thought about what would happen if you had data streaming into this and that people wanted to zoom in on what's happening now?
Definitely.
And then zoom out to see a reduced view of what happened in the past?
Yeah, definitely. Thank you. And so keep in mind that this is a 1.0. This was our first attempt, and it is just a static giant image, essentially. It was just to cover the zoom. Pushing Seadragon to the limits. The next step is, letting you import data that you're working on right now, visualize it in there, compare it next to something else, and like you were saying, future ideas, like you were saying, annotating, things like that. So we definitely want to make it a more dynamic experience in the next version. Right now, these are just examples that a lot of Walter picked out, his favorite episodes from history. But yeah, we should definitely talk. Thanks for the question. Hi.
Somewhat related question like in the Big Bang, a lot of the very interesting things at the Big Bang happened at the earliest seconds or sub-seconds and so forth.
Definitely.
And so can you, another example might be, I don't know, you go to the Revolutionary War and you want to look at what happened on a particular day and so forth. So can you do this sort of zoom through the time scales and fix your point and then change the time scale from within that?
Yeah, definitely. That's something planned. I'm just going to let this load. If it does load, maybe it won't. That's cosmic history, and that one is represented on a log scale to show the early seconds. Okay. Obviously, we do want to get to the day level where there's data available. So we went to the day level in the year 2000 just because that was acceptable. But yes, if there are records for a particular war and days, that would be great to include. The more dense we can make this, the more fun it's going to be to explore and learn. So thank you. That's planned.
First of all, this is just awesome. Curtis Wong has been telling me about this, and I hadn't seen it, and it's fantastic. And so I just have a question about how you get the information into it. So I think what I hear you saying is that you made a giant image.
Yeah.
And that's just, so my question is, do you have a plan, or is it part of the project that the images have some way to be dynamically generated so that people who want to add information can add information that becomes part of the giant scalable image?
Yes, thank you. And that's what's happening right now, is talks about, first of all, what data format do we pick, or do we create a new one? Do we pick an existing one where you can enter a table of information and it gets plotted in real time here? And then the other question about images is, I have a personal collection of pottery, for example, and it would be great to map them down on time. Yeah, we'd like to offer like a personal section where you can upload images. It wouldn't be on the web right away. It'd be just for you to look at. It might be copyright issues, just so you can put them in the time context.
Very much the way it works in Roland.
Yes, yep. We're working with Curtis, so we're in talks with Curtis, so we'll have a lot to learn. So.
Hey, Roland, awesome again. Is it clickable so I can then fire off onto other databases and journals and data sets elsewhere on the web?
Yeah, journals.
Is this my new interface to the internet?
Yeah, journals was definitely a very early thought. Like, how can we put articles in here so you can learn stuff? Hyperlinks obviously will do. Hyperlinks is not in this particular example just because we ran out of time. There was bigger challenges in making sure we could zoom through all of time right here. I have another example. Unfortunately, I can't show it right now, but we do actually, you could put a PDF in here. It doesn't just have to be an icon. You could actually read the individual pages in the PDF. We have the Zoom technology to do it. That's not a problem. So. Right. It would be like semantic zooming. So on a need-to-know basis. It wouldn't just be a tiny little thing always. As you zoom in closer, it would get bigger. So, this is a version 1 from April, so keep that in mind.
I'm interested. Oh, thank you. I'm really impressed by the design aspect of this. The way to, I imagine you must have spent some time to figure out what your references were going to be for folks to index into these various areas. I just wonder if you had any comments about that in terms of...
About sourcing? Or?
Well, just the design in terms of having it at all these scales, but being able to go into a particular time referenced by a meteor hitting or by something else.
Yeah, I mean, we picked out episodes that try to be appeal to a larger audience. You know, I mean, obviously some are really crazy and don't make sense to many people unless you spend some time reading about it. This design, you know, goes left to right, so it keeps it like a standard timeline. You know, if we were going to do this in Earth history, this would be a vertical up and down, like the way rocks and layers are done. So this example was to appeal to more people and make it more easy to comprehend. But there definitely are many design ways of doing. You know, we've got like Big Bang and logarithmic plot down there. We've got the present up in the top right corner. There's many ways of doing it. This is just one approach.
So do you imagine that users would at some point provide their own designs for how to do that indexing? Or
designs for indexing or ways of looking at it?
Well, ways of looking at it.
Ways of looking at it. Yeah, we think there should be at least a way of changing and saying, if I don't want to look at left and right, I want to look at up and down. Because people that work in climate, they need it up and down. They don't need it left and right. So there will be things doing, but we're working on them. Thanks. Mike's coming around.
Hi, I really love the talk. It's the second time I've heard it, so I still love it. I just first noticed the 4 intellectual property people credited on your last slide, and I was curious about that.
Uh-huh. Those are just people that Berkeley has a department which helps us put groups on campus in contact with partners. So they were just to help us get in contact. They got us in contact with Darren Green, right behind you, and that's how we got connected to the Live Labs team. So they were there to introduce us.
Is that because there's protected content on here, or?
I think
another way of saying it is part of their job is to broker into industry, and they did it really well. So we got a credit. Most of the time we don't credit those guys. Yeah, the IP people usually get in the way. Yeah. Well, they don't. At Berkeley, they help.
Yeah. Yeah. So I mean, yeah. But we're just so fortunate to be able to get it to this point. You know, I mean, it was just an idea that Walter and I were kicking around on the chalkboard, you know, after classes and stuff. So it's amazing to be able to show it to you today, even in this form. So.
Well, please join me in thanking both Roland and David. Tremendous work. Tremendous work.